This is Storm Surge from RENC, Renaissance Computing Institute in North Carolina. I'd like to introduce Brian Blanton and Paul Ruth. Thank you.
Thank you. This demo that you're going to see takes about 18 hours to run, so I hope that you had a very big breakfast. One of the things that I do is I study storm surge. Now, the physics of storm surge are fairly well understood. There's really not a lot of research into the physics. There's a lot of research into the impacts and how to deal with the impacts. And certainly things like Hurricane Katrina and more recently Hurricane Sandy have rung our bells in the way we perceive risk and the way we interpret information, and even more to the point from the science standpoint, how we compute or realize information that we can deliver further downstream to people that will hopefully be able to use it in a useful way. So one of the things that's true, which is true in the weather world, meteorological models are expensive to run, they're big, they're complex. A lot of storm surge models, in particular the one I'm going to talk about briefly, is actually very complex and requires a fair amount of horsepower to be able to run one simulation when we run it at resolutions that are really useful for very detailed analysis. So real-time, on-demand computation of storm surge. At the very end here, the last three bullets on the slide are the federal forecast cycle is 6 hours long. So every 6 hours, there's a new set of forecast information coming out. In order for our information to be useful, we have to be well within that 6 hours. If our information comes out at 1 minute to the cycle time, it's useless. It's old information and no one is going to care. So we spend a lot of time trying to get things within that particular forecast cycle. So the model in particular is called ADCIRC. It's FEMA approved. We use it quite extensively for flood insurance rate map calculations. This is if you live on the coast and you're paying flood insurance. The new maps were built based on information coming out of this model. And the bottom sequence of figures shows what the grids look like, the numerical grids. They're all triangles. There's millions of triangles in these grids. And as a consequence, they're very resource intensive. So unfortunately, one simulation is not enough because there's uncertainty in the hurricanes. I'm speaking specifically about hurricanes now, not so much extratropical systems. But one simulation isn't enough. There's uncertainty in the modeling, there's uncertainty in the input and the boundary conditions to these things. And of course, I mean, it's the real nonlinear world. If the world were purely linear, I mean, most of us would not really have interesting things to do. And so here's a picture of a research ensemble. These are 22 realizations of Hurricane Floyd. This is part of an NSF Hazard Seas project. And there's 22 members. The red line is the best of these tracks, and the blue line is the actual the actual track that Floyd took. So again, this is a research ensemble. There's a lot of spread here. Obviously, it's really hard to pin down what the optimal best track is with a very small number of ensembles here. And the hurricane itself is being generated by the WRF model, which is the standard. National Weather Service forecasting model. It's been tuned here to be more hurricane related. So each of those tracks we want to simulate. Oh yeah, that's right. So sorry. So the current limitations are that we have to be able to cram all these simulations into a finite number of resources. Typically they're local resources, and there's just not, it's very hard to get a full range of ensembles through in real time. So at this point, I'm going to introduce Paul Ruth from RENC, who's going to talk about the Genie solution to this kind of problem.
Yeah. So as Brian said, as Brian said, he is the oceanographer that knows how to run an ADCIRC and get the storm surge. And what I'm going to do, or what I've done, is help him get his application working on Genie in a reasonable way. So what does Genie give Brian and his application? Well, it's a federation of resources from all over the world, right? So that's great. It allows applications like Brian's that's urgent computing. So the hurricane comes, he only needs resources during a hurricane, and then when it's gone, he doesn't need very many resources. So what he can do is sort of cloud bursting of urgent of resources all over the available resources on Genie, and he can use these resources to perform his calculation. So this is great. Now he has access to resources that are far away from wherever he is. He's got lots of data to move back and forth. So one of the other things that Genie enables is the ability to transfer his input files to his remote computation facilities and then transfer the results back. And this is something that's not possible without without Genie or something like Genie. And it allows him to replicate his data and compute across geographic areas so he can get resiliency and some performance out of that. So what I'm going to say, and we started the run of the simulation supposedly 17 minutes before we were going to go on, but there was many delays. So we're a little bit behind. There's probably about one more thing that's going to happen. So whenever it happens, I'm going to stop and tell you what's going on. So Brian talked about his ensemble here. So his ensemble is 22 different storm tracks that he has to run the simulation for. Each one of these storm tracks itself is a high-performance parallel application using MPI, if you're familiar with that. In this case, we're going to use 32 compute cores, but it could use many more than that. So each one of those storm tracks is 32 compute cores. But of course, we have 22 of them to do. So what did we do? We created a Pegasus workflow using the Pegasus workflow management system. And this Pegasus workflow is an ensemble of many of these tasks that will be farmed out to remote resources all over Genie. And each one of these tasks is itself a parallel application that requires a lot of computation. And then there's a collector that collects all the results. Okay, so the demo we're doing today, and you can see this is the live demo. It's running right now. And this over here is just a description of what's going on because we couldn't put that on the screen. So we're using 11 different Genie sites. The one in UC Davis happens to be where the Pegasus workflow management system is running. And it is creating these tasks and sending them out to the remote sites to be processed. There's 10 remote sites all over Genie. We used only the US ones, but we could use other sites in any other federations to do the same thing. There's lots of, it's over here. There's lots of VMs, lots of cores. It's one of the larger slices, I think, that has been run on Genie, and it's actually doing something useful, which is great. We also are collaborating with another slice that is currently running, also one of the bigger slices running on Genie right now, and this is the Intelligent Data Movement Service by Ezra Kissel. He has his own demo, so I'm not going to talk about what it is. Just know this is a very large slice. It's also running on Genie. It kind of behaves like a really fancy Dropbox for large scientific data staged all over Genie. So from wherever we are in Genie, we can push data into Ezra's system and then pull it out on the other side. He does it in an efficient way and replicates it and so forth. Right? So we're using his system. But we're only using it in the sites that have capabilities of connecting to it. So but 5 of our compute sites have access to it, 5 don't. This doesn't matter to us. Where we can connect to his system, we'll get the data from him, and where we can't, we use our 1 gigabit links that we've been standing up all over Genie. Right. Whoops, go back. So the next thing I was going to do is show the actual slice in action. So what should be happening now, and there's one more that's going to happen in a minute, is so the workflow starts at UC Davis. Tasks are created, and they're shipped off all over the infrastructure. So for example, a task might get shipped from Davis to Florida International. And then what happens is Florida International starts to execute its task. First thing it needs to do is it needs to fetch its data. So it goes out and it fetches its data. Florida International does not have IDMS, so it's going to fetch it from Davis directly. It's going to pull the data in. When that happens, we would see on this chart here a spike in network utilization, which you probably saw a few happening earlier while we were talking. That transfer will happen. When that transfer is done, it will stage the data within the set of compute cores that it has at FIU, and then it'll kick off the MPI job, which will use all 32 cores to do calculations, and that's what we're seeing here. This is actually 81 lines representing the VMs all over these sites. Many of them have already moved on to their calculation phase. There's at least one more down here that hasn't yet, and we should see a spike up here hopefully before we're done talking, which will then correspond to a set of VMs that go up and spike on the CPU side. Watch for that while Brian's talking. I was going to let Brian run this one. I'll let you forward it because it's your video.
Okay.
So Brian's going to talk about what he does with the results of this data when it's done.
All right, great. So each one of these 22 ensemble members looks like this. It's a hurricane. It's going over the ocean. It's causing storm surge. And the storm surge in this case is going to be the colors that are near the coast. As the storms get nearer, obviously the water has to pile up. This is kind of what they look like. So boom, it's hit shore. This fictitious Floyd made impact near Wilmington, North Carolina, which was in fact about where it did. Now, so each one of those simulations has its own response to it. So because these are probabilistic simulations in terms of generating the hurricane scenarios, we can create a probability surface essentially from all of those members. Here are 6 of those 22 members, just to show you on the top that some of these hurricanes don't impact North Carolina, so we will throw them away. Some actually do make impact in North Carolina, and we'll retain those to be able to do something like the analog of the 90% chance of rain. So these are, research predictions in retrospect, obviously. It's easy to predict the past, by the way. And so 90%, this on the lower, on your left, is the water level that's going to occur based on this ensemble at a 90% chance. So any place in this area has a 90% chance of the water equaling or exceeding essentially 12 feet. That's the analog in our world to something like a 90% chance of rain, and the total is going to be roughly 3%. So that's where we want to go. The difficulty is, again, go back to this slide, 22 members is not enough to characterize the uncertainty in really virtually any forecast system, but particularly in something like hurricanes, which are very difficult to deal with. What we really want to do is this. So here's a picture of an ensemble of hurricane tracks generated by the National Hurricane Center. This is, again, a retrospective 2010 hurricane. There are hundreds of ensemble members here. What we really want to do is take that ensemble and run it through the same high-resolution storm surge model to be able to get at really that weather analog and have relatively tight confidence bounds on the predictions that we would make. Now, again, we're in the research mode. We're not a forecast agency, so we then have to translate that information into something that the Hurricane Center, for example, could use as an additional information, and that's a whole different bottleneck. So then each of these ensemble members is going to get farmed out to one of these, in this case, 32-core VM, and go about its business. This is where we're at. We can't do this yet because we need essentially hundreds of these slices available, and to do it in real time is an even bigger challenge. Real time meaning within that 6-hour forecast cycle. So I'm just going to wrap up here, Paul, if you don't mind. So the AdSurge storm surge model here is the application we're using, and it's being broadcast in very novel ways across the Genie network. And Genie is an ideal test bed for this kind of problem because it's a highly relevant problem. It's a risk analysis problem. It's a decision-making problem. And sort of using Genie, what we'd really like to do is be able to put Genie infrastructure into traditional leadership class infrastructure, as well as the mid-size infrastructure that's a lot more prevalent, but not necessarily as easy to get to. Other funded projects at RENCI with our collaborators, including other domain scientists, include genomics and astronomy, medical and health data analytics and predictive capabilities, as well as a different type of climate problem and one version of energy physics in the neutron science space. So I believe that is the extent of our demo, and we made it. So these are our partners and some of the funding sources, so we'll leave it at that.